We arrived to the last session of this very gorgeous and beautiful conference. My name is Muhammad Yunus, and this session we have three interesting talks. The first one will be presented by Professor Tubino, and it's entitled An Equivalent Nonlinear Beam Model for the 3D Dynamical Analysis of Shear-type Buildings from the group of University of Genova. So, Professor Tubino, you can start.
So thank you, Mr. Chairman. Good morning, everybody. The research I am presenting has been carried out in collaboration with Professor Piccardo and with Professor Luongo. So we know that tower buildings are usually slender structures, and so they can be susceptible to vibrations induced by wind or earthquake. So even if detailed numerical analysis are not in question for the final design of such structures, semi-analytical approaches can offer interpretative advantages in terms of comprehension of the structural global behavior. And so simple models can be useful for preliminary analysis under wind and earthquake actions. For this reason, we introduced a one-dimensional shear torsional equivalent beam model, and we applied it for the aeroelastic analysis of tower buildings. So in this presentation, at first, I will briefly describe the structural model. I will introduce the equations of motion, and then I will focus on the aerodynamic model, which is different for galloping and for the analysis of vortex-induced vibrations, and then I will show some numerical application. The monodimensional equivalent model is considered as a polar continuum with the rigid local structures, which is assumed as unflexurable and clamped at one end. And it is described by four scalar configuration variables, which are the three displacements and the twist. And correspondingly, we have four exact strain measures, which are the axial and the shear deformations and the torsion. External forces and couples can act on the beam, and we consider as stress measures the internal contact forces, which are normal, shear and moment, and so we write scalar balance equations where external forces are the sum of aerodynamic, inertial and damping terms. So in order to introduce the hyperelastic law of the one-dimensional equivalent model, we start from a three-dimensional model of the tower building. In particular, the macroscopic shear strain of the one-dimensional model is produced by bending of the columns, accompanied by small rotations of the floors, which are assumed as rigid. So in the refined three-dimensional model, when a floor moves with respect to the adjacent one, the columns undergo axial strains, which depend on their position with respect to the center of rotation. However, the sum of the axial forces must be zero. So even if the average normal force is zero, the individual values are not zero, and so an elastic energy is stored in the cell. So the nonlinear hyperelastic law is introduced starting from an expression of the density of elastic energy that takes into account the stretching of the columns. In particular, an axial displacement in the one-dimensional model is allowed to occur. However, this is condensed by requiring that the total axial force is zero. So without going into details, the total elastic energy of the cell is obtained by summing up the energy of the columns, where the energy of the columns take into account axial, flexural, and torsional contributions. So by applying the green law, we obtain a constitutive law, which is made up of linear and nonlinear terms. In particular, the constitutive law couples shear and torsion, and the coupling depends on the position of the flexural center. So if we consider together the kinematics, the dynamics, and the constitutive law, we can build a continuum model associated with boundary conditions, which are a clamp at the base and the free end at the top. So in order to discretize the model, we separate time and space variables by means of the solution of the free linearized model. And so we obtain a system of second-order differential equation which can be rewritten in non-dimensional form, where linear, quadratic, and cubic forcing terms appear. Furthermore, a mechanical coupling is present, which is dependent on the position of the flexural center with respect to the center of rotation. In order to complete the model, we have to introduce a model for the aerodynamic actions. In particular, two different models for aerodynamic loads have been considered for galloping and for vortex-induced vibration analysis. For galloping, the quasi-steady theory is assumed to be valid. This is valid if vortex shedding frequency is much higher than the structural natural frequency. In this case, the aerodynamic actions can be expressed as functions of the relative wind velocity. And so polynomial expressions for the components of the aerodynamic forces can be obtained by expanding the relative velocity and the angle of attack in Maclaurin series of the structural velocities. On the other hand, if quasi-steady theory does not apply, so if vortex shedding frequency is close to the structural frequency, and in particular the structure is characterized by a low Scruton number, then quasi-steady theory does not apply, and the across-wind motion interacts with the aerodynamic force, and vortex shedding frequency locks on to the structural frequency. That's what is commonly called lock-in phenomenon. In this case, in the literature, different force models have been proposed. However, we use a van der Pol nonlinear model, which has been introduced in the literature, where the coefficients of the model are aerodynamic parameters which depend on the non-dimensional mean wind velocity and are determined experimentally. So we will adopt these two different models to deal with the two different problems. So starting with galloping analysis, at first we analyze the critical condition by studying the linearized discrete model where aerodynamic damping and stiffness terms appear. We write equations of motion in the state space form, and we evaluate the complex eigenvalues and eigenvectors of the state space matrix as functions of the non-dimensional mean wind velocity, which acts as a bifurcation parameter. Then the nonlinear bifurcation analysis is carried out, studying the behavior of the system in the neighborhood of the critical condition. In particular, the velocity is perturbed around its critical value, and the solution is obtained by applying the multiple scale method. In particular, I want to focus on the generative solution, which depends on the critical eigenvector of the state space matrix, and then the amplitude modulation equation is obtained by imposing the solvability condition at the second order equation. And so we obtain the amplitude of periodic oscillations of the tower building as functions of the non-dimensional mean wind velocity. Concerning vortex-induced vibration, the governing equation is different, and also in this case, aerodynamic damping and stiffness terms appear, and moreover, aerodynamic and mechanic cubic terms, forcing cubic terms, are present. In this case, we order the parameters based on the physically small parameter ν, which is the mass ratio, and we assumed that the structural damping and the cubic aerodynamic and mechanical forces are small of the same order as epsilon. So we obtained a solution applying the multiple scale method, considering as a generating solution as a function of the eigenvector corresponding to the mainly lateral vibration mode. Also in this case, we obtained the amplitude modulation equation by imposing the solvability condition, and so we were able to obtain the amplitude of periodic oscillations and also the frequency correction. So we applied this model in order to evaluate the galloping and the vortex-induced vibration behavior of an ideal building with a square cross-section which is excited along a symmetry axis. Concerning aerodynamic characteristics, they are taken from literature papers based on wind tunnel tests. So, concerning galloping, at first a linear bifurcation analysis is carried out, and in particular the critical mode components and the critical non-dimensional wind velocity are evaluated of varying the eccentricity of the flexural center with respect to the centroid and the frequency ratio between the torsional and the shear mode. And then post-critical analysis is carried out, and the amplitude of the post-critical oscillation is evaluated for specific configuration of the building. Concerning vortex-induced vibration, only a post-critical analysis is performed, and the amplitude and frequency of the oscillation at lock-in are evaluated for a specific configuration of the building. This is really a new part of our research that has been carried out in the very last period. So, starting from galloping, we detected a single op bifurcation with a critical mode which is composed by a coupling between shear and torsion. And in the left-hand figure, we plot the crosswind component and the torsional component of the critical mode as a function of the eccentricity of the flexural center and of the frequency ratio between torsional and the shear mode. And we can see that for zero eccentricity, the torsional component is obviously null, while on increasing eccentricity, the mode becomes coupled between lateral and torsional vibration, and this coupling tends also to increase on decreasing the frequency ratio. The right-hand figure shows the ratio between the critical velocity and the Denartog limit evaluated by assuming a purely crosswind vibration. And we can see that this ratio is almost always higher than 1, meaning that the coupling between shear and torsion increases the stability of the system. These are the results of post-critical analysis. We considered 3 different columns configurations, giving rise to different behaviors. In particular, we compare the post-critical amplitude evaluated in purely crosswind motion, which is the gray line, with the post-critical amplitude taking into account the coupling and taking into account both aerodynamic and mechanical nonlinearities, which is the solid line, and the critical amplitude taking into account only aerodynamic coupling, which is the dashed line. In this first configuration, we see that the coupling with torsion has a stabilizing effect because the critical velocity increases, and nonlinear mechanical terms tend to decrease the post-critical amplitude. In the second configuration, we have always a stabilizing effect of the coupling with torsion, but mechanical nonlinearities do not affect the post-critical behavior, while in the third case, we have that the coupling with the torsion decreases the critical value, and mechanical nonlinearities have a very small effect on the post-critical amplitude. Concerning the vortex-induced vibration analysis, we show a very preliminary result. In this figure, we have the post-critical amplitude in the coupled and uncoupled cases, and we see that in this case, coupling has a very, very little effect on the post-critical amplitude. However, the obtained results are quite in good agreement with experimental results from the literature. And concerning the effect on the frequency, we can see that aerodynamic terms have a softening effect, producing a decrease of the vibration frequency in the post-critical regime, while mechanical effects, mechanical nonlinearities, have an hardening effect, producing an increase of the frequency of vibration. So, in conclusion, we introduced the nonlinear equivalent model for the analysis of shear-type buildings, which allows to take into account the coupling between shear and torsion, And this model has been applied for the galloping and vortex-induced vibration analysis of these buildings. And we applied it to a square building excited along a symmetry axis. Concerning galloping, we saw that coupling between shear and torsion usually increases the stability limit, and nonlinear mechanical terms reduce the post-critical oscillations, while concerning vortex-induced vibrations, the main effect that we observed is the hardening effect of the nonlinear mechanical terms. While we have some questions that we would like to solve. First of all, we would like to refine the equivalent model, taking into account also the presence of shear walls. And then we would like to study a little bit more the problem of vortex-induced vibrations, maybe using a different model for vortex-induced forces based on a wake oscillator model. And also, we would like to use from a technical point of view the results that we obtained in order to evaluate, for example, accelerations at the top of the building to deal with the serviceability problems of tower buildings. So I thank you for your attention.